All right, so in the last module, we introduced the position and momentum operators, and we discussed how to calculate expectation values of these operators um, using some very simple wave functions. Okay, so we discussed the X and the P operators, and let us quickly recap that the P operator has a very specific representation. This is minus IH bar ddx. Okay, and based on your tutorial 8 knowledge, you also know that the operator minus I ddx is actually a Hermitian operator. It's a Hermitian operator. Okay, and let's also recall that Hermitian operators or Hermitian matrices, if you are comfortable with linear algebra more, have two very important properties. Their eigenvalues are real and their eigenvectors or eigenfunctions, if their operators are orthogonal. Okay, both these properties are of central importance in quantum mechanics. To illustrate, we will start with a very simple example of a finite dimensional matrix, and we will try to understand what this orthogonality gives us. Okay, why is it that these two properties are very important in quantum mechanics? A complete answer to this question we can obtain only after we introduce the next postulate, but we will try to milk this mathematics as much as possible and try to understand what this gives us. Okay, so let me illustrate this with a very simple example. And along the way, I want to introduce you to the concept of basis vectors and basis functions. So let's take a very simple Hermitian matrix, 0, I, minus I, 0. Okay, so obviously if I transpose it and complex conjugate, I get the exact same matrix back. So this is clearly a Hermitian matrix. So what are the eigenvalues of this matrix? The eigenvalues I can obtain by solving the characteristic equation H minus lambda I, determinant is equal to 0. This is basically the determinant minus lambda I minus lambda equal to 0. And you can clearly show that this is basically lambda squared minus 1 equals 0, which gives me lambda equals plus minus 1. Okay, so you see that these are real eigenvalues. Even though we started with a matrix that has complex entries, since it's Hermitian, your eigenvalues are guaranteed to be real, as we proved in the last tutorial. Okay, so what are the eigenvectors of this matrix? Well, the eigenvectors you can obtain by plugging in the eigenvalues one by one in the eigenvalue equation. So I'll plug the first eigenvalue, which is plus 1, and I'll call this eigenvector some x1, x2 equals lambda 1, x1, x2. Lambda 1 is just 1, so this is x1, x2. Okay, you can solve this equation. There's two very simple equations. The first equation is 0 times x1 plus I times x2 is x1. So this gives me I x2 equals x1. The second equation will be very similar. Okay, so my first eigenvector is such that the second entry is minus I times the first entry. So I will choose my first vector. I can choose the first entry to be anything I want. So I'll choose this to be 1. And if I choose the first entry to be 1, the second entry has to be minus I. Okay. Now, if I were to normalize this, what is the normalization? So I will choose this normalization to be some A, which can be complex, and 1 minus I. Normalization in this case would mean x1, x1 dagger, x1 is 1, which means modulus A square times 1 minus I has to be equal to 1. And if you solve this, you will actually get A is 1 over root 2. Okay, so the first eigenvector, the first normalized eigenvector I can write as 1 over root 2, 1 minus I. And you can quickly show that the second eigenvector corresponding to the eigenvalue minus 1 would be 1 over root 2, 1 I, following the exact same prescription. Okay, so these are the two eigenvectors. So what is the second property of Hermitian matrices? The second property is that the eigenvectors are orthogonal to each other. Are these orthogonal to each other? Well, let's check. So what is x1 dagger x2? x1 dagger x2 is there is a 1 over root 2, 1 over root 2, which gives me 1 over 2. x1 dagger is x1 transposed complex conjugated. This gives me 1i. x2 is 1i. And this is 1 over 2 times 1 minus 1, which is properly 0. So the two eigenvectors are orthogonal to each other. This is the statement that they are in some sense perpendicular to each other. Okay, all right. So it is no surprise that the eigenvectors are orthogonal and the eigenvalues are real. But what does this give us? And why should we belabor this point? So notice that the eigenvectors being orthogonal has a very interesting import. So let us step back and talk about basis vectors. Remember that we also talked about the whole notion of basis vectors and basis functions in our discussion on electrodynamics, particularly when we solved the Laplace equation and discussed the eigenfunctions of Laplace equation, if you remember. Basically, in three-dimensional Cartesian coordinates, so you have your z-axis, y-axis, and x-axis. You have three basis vectors. The three basis vectors are I, j, and k, right? And basically, the use of the basis vectors is that they are orthogonal to each other in the sense that I dot j equal to 0 and so on and so forth. They are properly normalized. I dot I is 1. And any vector A can be written in this three-dimensional space as something times the I vector plus something times the j vector plus something times the k vector. Okay, so any vector in this three-dimensional space can be written as a linear combination. Any random vector is a linear combination of the basis vectors I, j, and k, right? So I, j, and k has this remarkable property that they are the basis vectors. And we are all very used to this notion of I, j, k being the basis vectors. We also call them unit vectors, but basis vectors is a better choice of words. All right. But there is nothing sacred about I, j, k. Okay, I can also take any other linear combination of I, j, and k. And as long as this new combination satisfies the property that they're all orthogonal to each other and they're all properly normalized, they can also serve as basis vectors. For example, if I choose a 2D subspace of I and j, for example, or I and k, whatever you want, I can still stick with I and j, but I can equally go on to some new basis vectors, ex and ey, which is 1 over root 2, I plus j, and 1 over root 2, I minus j. Okay, so you can verify yourselves that the norm of the length of ex is 1 because the length of I is 1, the length of j is 1, and the 1 over 2 cancels the 2. And these two are orthogonal to each other because I dot I is 1, j dot j is 1, but 1 minus 1 is 0. So ex dot ey is also 0. So ex and ey are also perfectly good unit vectors in the two-dimensional subspace spanned by I and j. Okay, so there is no fundamental reason one chooses one over the other. Usually the choice is driven by whichever is more convenient for the problem at hand. Okay, so how does this all tie up with our discussion on Hermitian matrices? Well, Hermitian matrices also give us eigenvectors, and we can normalize the eigenvectors, and these eigenvectors of Hermitian matrices have the property that xi dot xi is 1. Okay, this is not automatic, but you normalize them. Okay, and they also have the nice property that the eigenvectors are perpendicular to each other or orthogonal to each other. Xi dot xj is 0 if I is not equal to j. So the eigenvectors of a Hermitian matrix can be used, eigenvectors of a Hermitian matrix can be used as a set of basis vectors in that space. What does this mean? Well, let's go back to our simple 2 by 2 example. We started with h is 0, I minus I and 0, and we got two eigenvectors. X1 is 1 over root 2, 1 minus I, and x2 is 1 over root 2, 1I. Okay, so if you regard this matrix as being defined with the usual I and j unit vectors, then basically what we are saying is x1. So if you regard this I vector as 1 along the x-axis and 0 along the y-axis, and the j unit vector as 0 along the x-axis and 1 along the y-axis, then we are basically claiming that these eigenvectors x1 and x2 can be written as 1 over root 2 times 1, 0 minus I over root 2 times 0, 1. Okay, so we are basically saying that these eigenvectors can be thought of as linear combination of the basis vectors in this space, which is 1, 0 and 0, 1. Okay, but we don't have to stick with this choice of basis vectors. We can also very well use x1 and x2 themselves as basis vectors. In other words, I can write any other vector. Let us say this vector has some components a and b as, of course, I can write this as a times 1, 0 plus b times 0, 1 in the 1, 0, 0, 1 basis choice. But I can equally well write the exact same vector a and b as something times my x1 vector, I'll put alpha over root 2, plus something times my x2 vector. Just like this is a valid equation because I'm expressing this random vector with components a and b as a linear combination of the basis vectors 1, 0 and 0, 1. I can express the exact same vector as a linear combination of the basis vectors 1 minus I and 1I. Nothing happens to the vector. The vector is a vector. Okay, all we are doing is changing how we represent this vector in two different choice of bases. Okay, so this is all probably things that you already know in finite dimensions. Any vector alpha a vector can be written as a linear combination of the basis vectors of any Hermitian matrix in this particular space. Suppose if we are living in a 5-dimensional space, and if I have a 5 by 5 Hermitian matrix, I can diagonalize this Hermitian matrix and write down what its eigenvectors are. And in this 5-dimensional space, I can express any 5-dimensional vector as a linear combination of the eigenvectors xi of this Hermitian matrix with properly chosen coefficients alpha I. Okay, for example, in this equation, you would have to solve for alpha and beta in terms of a and b. And once you know what alpha and beta is, I can always express any vector as a linear combination of the basis vectors. Okay, so far so good. So what happens if you have functions? Well, the exact same thing holds for a function. So for a differential operator or a Hermitian operator, you have not eigenvectors, but eigenvalues and eigenfunctions. Okay, and these eigenfunctions are, you can make them normalized to unity. Okay, normalization again is in your hands, but these eigenfunctions turn out to be orthogonal to each other. Okay, and we can use the exact same knowledge that we gained in finite dimension, like any vector can be written as a linear combination of the basis vectors, and we can take any Hermitian operator and figure out its eigenfunctions. These eigenfunctions are orthogonal, and we can write any other function as a linear combination of the eigenfunctions of a Hermitian operator in that particular space. Okay, we will try to illustrate what this means using the P operator that we discussed yesterday. Remember that the P operator again is given by minus I h bar ddx. And yesterday we showed that the eigenfunctions of P are given by psi P equals A e to the I px over h bar. Okay. All right. So first of all, we have to understand what orthogonality even means for a function of this sort. First of all, notice that this is not square integrable. Not square integrable. Okay. What does this mean? If I take psi p star, psi p, excuse me. Okay. And I try to integrate this from minus infinity and infinity, this does not make sense. Okay. This does not make sense. It blows up. Okay. Because it's simply the integration of dx from minus infinity and infinity. So this is not a normalizable wave function. Does this bother us? Not quite, for reasons we will talk about in a second. Let us push forward and ask if these are actually orthogonal. Normalization or square integrable simply means I take the wave function corresponding to momentum p, take the star, and the wave function corresponding to the momentum p and take the star and see what happens. Orthogonal means I take two different eigenvectors or two different eigenfunctions. In this case, since IP is some A, I'll have a mod A square integral minus infinity to infinity. I'll take psi p prime star psi p dx and ask if this is equal to 0 in just like we had it for vectors. What is this? This is equal to a square minus infinity to infinity e to the p psi p prime is e to the minus I p prime x over h bar. This is e to the plus I px over h bar dx. So this quantity turns out to be mod a square integral minus infinity to infinity e to the I p minus p prime x over h bar dx. This is equal to 0. Well, it is not 0 in the traditional sense like you would define for a vector, but you would immediately recognize what this integral is. This integral is basically the definition of a delta function. This is a delta function in p minus p prime. So this integral is actually equal to a square times 2 pi h bar delta p minus p prime. Remember, we talked a lot about delta functions at the beginning of this course when we discussed electrodynamics. Delta of p minus p prime has the nice property that if I integrate any function f of p delta p minus p prime dp, it simply picks out the value of the function at p prime, because by definition delta function is 0 for any value of p which is not equal to p prime. Okay, so the eigenfunctions of a momentum operator are actually orthogonal in the sense that they are delta function orthogonal. Okay, which is as it should be, because these are functions, these are not just vectors. A convenient choice of A is 1 over square root of 2 pi h bar, so that we can absorb this factor of 2 pi h bar in the definition of the wave function, eigenfunction itself. So I can define the eigenfunctions of the momentum operator as A e to the IPX over h bar, which is equal to 1 over square root of 2 pi h bar e to the IPX over h bar. Okay. Now this choice of A is not expressly necessary. We can pick any other choice of A itself, but this makes it very convenient because with this choice of A, integral psi p star, psi p prime star, I'll write this again, sorry, minus infinity to infinity, psi p prime star of x, psi p of x dx is automatically equal to delta p minus p prime. Okay, so you don't have any pesky factors of 1 over 2 pi h bar on the right hand side because it is cancelled between the a square here, the a square here, and the 2 pi h bar. Okay, so that is the advantage of this normalization. So just like any vector can be written as a linear combination of the basis vectors of a Hermitian operator, any function of momentum can be written as a linear combination of the basis functions of the Hermitian operator P. So what does this mean? Suppose if you have some random function of P, f of P, I have to write this as a linear combination of the basis functions. Now I know how to write any vector as a linear combination of the basis vectors. So this is how I would write it, yes? But here I have a continuous function, I have a continuous variable P, I don't have a discrete variable I, so the summation has to be replaced by an integration. And these coefficients are also now continuous functions of P. So the equivalent statement for the case of a continuous function is any function of P can be written as, now choose proper coefficients alpha of P, basis function psi p of P dx. Okay, so this is the equivalent statement in the case of continuous functions and the eigenfunctions of the momentum operator. It simply says that any function of P can be written as a linear combination of the basis functions of P. Okay. This is actually extremely useful in quantum mechanics, and we will discuss the usefulness of this in quantum mechanics once we discuss the measurement postulate and then talk about the superposition principle. But for now, take it as a continuum generalization of whatever you know about Hermitian matrices. Okay? All right. So given this information, how can we proceed and construct other operators? So what is the fundamental importance of X and P operators? And how do we, for example, look at the kinetic energy operator or the Hamiltonian operator and things like that? Okay. So we will talk about that briefly. Okay. So let us take the kinetic energy operator. So remember that kinetic energy in classical mechanics is defined as 1/2 mv square, right? In classical mechanics. So I can write this as p square over 2m, where p is momentum, mass times velocity, which is the momentum. So in quantum mechanics, as we discussed in the second postulate, every observable in classical mechanics becomes a corresponding operator. So we should not talk about kinetic energy of a particle, but we should talk about what are the possible values of the kinetic energy operator. Now, what is the possible values one can measure of the kinetic energy operator T hat? T hat is given by 1 over 2m P hat square. Okay. Now, what is P hat? It is minus IH bar ddx. So this is 1 over 2m minus IH bar square d square dx square. Okay. In other words, the kinetic energy operator in quantum mechanics is given by minus h bar square over 2m d square over dx square. So this is a very important operator. Okay. So how about, suppose if you want the expectation value of this in when you have some wave function psi, how would you calculate it? You will calculate it by sandwiching this operator between psi star, let us say minus infinity and infinity. This is okay, sandwiching this operator between psi star and psi. So this is given by minus h bar square over 2m integral minus infinity to infinity psi star d square psi over dx square dx. Okay. Now, if you do a partial integration, you would actually find that this is equal to h bar square over 2m integral minus infinity to infinity dx d psi dx mod square. Okay, I'm throwing away the boundary term because we will assume that we are dealing with wave functions that are square integrable, so they all go away to 0 at x is equal to infinity and minus infinity. And you would actually see that this is a manifestly positive quantity, as it should be, because the kinetic energy is a manifestly positive measure. Okay. In 3 dimensions, the kinetic energy operator is still p square over 2m, but in 3 dimensions, the momentum operator is actually given by minus ih bar times the del operator, not just ddx, but it is 3 directions, ddx, ddy, and ddz. We have already introduced what the del operator is, so I will not talk about this further. Okay. Another important operator is the total energy operator, the operator that measures the total energy. Again, the total energy in classical mechanics is kinetic energy plus potential energy. So this is equal to 1/2 mv square or p square over 2m plus potential energy v of x. In quantum mechanics, this is replaced by an operator for the total energy, and this operator is a very important operator, as I told you the last class also, called the Hamiltonian operator. This is a measure of the total energy. This has the symbol H. H is given by the kinetic energy operator p square over 2m plus the potential energy operator v of x hat. Okay, well, what is this v of x hat? So suppose if we have some potential energy, let's say you are looking at a simple harmonic oscillator. Simple harmonic oscillator. Okay. In classical mechanics, the potential energy of a simple harmonic oscillator, as you very well know, is 1/2 m omega square x square. But in quantum mechanics, this becomes a corresponding potential energy operator with x replaced by x hat. So this becomes 1/2 m omega square x hat square. So in the case of a simple harmonic oscillator, I will have the Hamiltonian as p hat square over 2m plus 1/2 m omega square x hat square. Okay, we will talk about this Hamiltonian later in the course. But this is how you construct other operators in quantum mechanics. So the reason we talked about the x operator and the p operator at the beginning is because many other operators, in fact, almost all the other operators can be thought of as some combination of the x operator and p operator. Okay. For example, the angular momentum operator L hat is R hat cross p hat in quantum mechanics. Okay. So it seems that everything is quite straightforward. So whenever you see something like x or p in quantum mechanics, you simply substitute x hat and p hat and you get the corresponding operator in quantum mechanics, as long as you're talking about a physical observable. But you have to be a little careful in quantum mechanics. I'll mention just one caveat. Suppose if you have a classical observable, okay, that depends on some combination x times p. Okay, so for example, like this angular momentum operator that is it depends on the combination of x and p. Let us say that you have x times p. Okay, this is, of course, I'm not claiming this is an observable in classical mechanics, but suppose if you have something, then if you want to make this an operator in quantum mechanics, you should not simply write x hat p hat. Okay, the reason you cannot simply write x hat and p hat is because x hat, even though x is a Hermitian operator and p is a Hermitian operator, x times p is not a Hermitian operator. Okay, so you have to be a little careful because all operators in quantum mechanics are Hermitian operators. So the postulate specifically tells you that for every observable in classical mechanics, there is a corresponding Hermitian operator in quantum mechanics. The reason we are dealing with Hermitian operators is because their eigenvalues are real. This is the first important point, and this is deeply connected with the measurement postulate of quantum mechanics, which we will discuss in the next module. So since x hat p hat is not real, any combination like x times p in classical mechanics should be replaced with a corresponding operator, the symmetrized version of x times p. Okay, x hat p hat is not a Hermitian operator, but you can quickly verify that xp plus px is actually a Hermitian operator. Okay, so barring such caveats, the operator in quantum mechanics can be simply obtained by promoting the classical observables p and x to the corresponding quantum mechanical operators p hat and x hat. And once you have the operator, you now have a prescription to understand what the average value of this operator is, or rather the proper terminology is expectation value of the operator given a particular choice of wave function. So in the next module, we will start talking about the postulate of quantum mechanics that is in some sense the most troublesome from a classical standpoint, and how some of these mathematical uh, knowledge that we have gained is actually very useful once we discuss the next postulate, which is the measurement postulate. So for now, we will stop here, and we will continue in the next module with the next postulate of quantum mechanics.